All you need to know about Leonardo Fibonacci and Fibonacci sequence.
The life of Fibonacci. He was also called Leonardo Pisano, English Leonardo of Pisa, and his original name was Leonardo Fibonacci. He was born in 1170 in the town of Pisa and died in 1250, presumably also in the town of Pisa. He was a medieval Italian mathematician who wrote books like Liber Bacci, which was published in 1202, Book of the Abacus, the first European work on Indian and Arabian mathematic systems. Little of the life of Fibonacci is known other than his achievements and academics. His father, Guglielmo, during his boyhood, was a peasant merchant that was appointed to oversee the community of peasant merchants in the port of Bokia, Algeria. Then he was sent to study calculations with an Arabic master in that region. He later on went to travel to various places such as Egypt, Syria, Greece, Sicily, which was in Italy, and Provence, which was in France. Fibonacci later on ended his travels at around the year 1200 and returned to Pisa. There, he wrote a number of important texts that was vital to the revival of ancient mathematical skills, and he made significant contributions of his own. Fibonacci in the time did not have the printing press, so all the books he had to write were by hand. And every single copy of Liber Bacci, which was published in 1202, Practica Geometriae, which was released in 1220, Flos, which was released in 1225, and Liber Quadratorum, which was dedicated to Frederick II in the meeting. Given that relatively few made copies have ever been produced, we are fortunate to have access to his writing in these works. However, some texts that he wrote are unfortunately lost. His book on commercial arithmetic, D minor Guisa, is lost, as is his commentary on Book X of Euclid's Elements, which contained a numerical treatment for the irrational number. With the publishing of Liber Bacci drew the attention of the Holy Roman Empire, Frederick II, which owned northern parts of Italy in the current day, and he was invited to meet him in Pisa. He was also a major contributor to the number theory, with his dedicated book to Frederick II, Liber Quadratorum. Other than the efforts in expanding knowledge of Hindu-Arabic numerals, he is largely known today for the Fibonacci sequence, which was developed from a question in the book Liber Bacci. A certain man puts a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair, which from the second month on becomes productive? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, 8 plus 13 equals 21, 13 plus 21 equals 34, 21 plus 34 equals 55. These numerics put together in a successional square would form the golden rectangle.
What is the Fibonacci sequence? The Fibonacci sequence is a series of numbers. So basically, 1, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. So here's an example. Well, blank is found by adding blank. So here, 2 is found by adding 1 and 1. And 3, right here, is found by adding 1 and 2. And let's just take 2 and 3 here and make a 5. 5 is found by adding 2 and 3. And this keeps on going on because the Fibonacci number, well, just keeps on going on forever. We could actually make a chart to place the Fibonacci numbers. So right here, let's put the n as the number. Yep, for the number. And x for the value. So right here, it's 0 and 0. And 1 is also 1. 2 is 1. 3 is also 2. And 4 is with 5. The 3 here. And 5 with 5. 6 right here with 8. And 7 with 13. And this will keep on going on forever because the Fibonacci sequence would never end.
Fibonacci's rabbit problem. A single newly born pair of rabbits, one male and one female, are put in a field. Rabbits are able to mate at the age of 1 month, so at the end of its second month, a female can produce another pair of rabbits. Rabbits never die, and this is a condition, and a mating pair always produce one new pair, one male, one female, every month from the second month on. The real question, what is the number of rabbits in a year? To solve Fibonacci's problem, we'll let f bracket n bracket be the number of pairs during month n. By convention, f bracket 0 bracket equals 0. F bracket 1 bracket equals 1 for our new first pair. F bracket 2 bracket equals 1 as well, as conception just occurred. A new pair is born at the end of month 2, so during month 3, f bracket 3 bracket equals 2. Only the initial produces the offsprings in month 3. So f bracket 4 bracket equals 3. In month 4, the initial pair and the month 2 pair breed. So f bracket 5 bracket equals 5. We can proceed this way, presenting the results in a table. At the end of the year, Fibonacci has 144 pairs of rabbits. However, this solution only works if we were to assume that the rabbits are able to mate at the age of 1 month and pregnancy takes 1 month. At the end of its second month, a female can produce another pair of rabbits. Third, the rabbits never die, and a mating pair always produces one new pair, one male, one female, every month from the second month. Therefore, we can say that this problem is not quite a realistic one. First of all, rabbits die of old age. Second, you can't say that the mating pair gives birth to the pair of male and female all the time. There is probability it could be two males and a female. The list goes on. With the descriptions of Fibonacci's life over and the explanation of the patterns in the Fibonacci sequence, it's explained, I will now demonstrate how to use the Fibonacci sequence to create the golden rectangle. First, you start off with the 2 units of 1 by 1s for the first 2 terms of 1, 1, 2. The Fibonacci sequence. Then after that, 2 by 2, 1, 1, 2, 1 plus 1 equals 2, 1, 1, 2, 3, 5, 8, 13, pardon my horrible drawing, 21, and 34. You can keep on going on with the numbers, but these squares I decided to draw are bigger, so I'm just going to stop at 34. And you'd use the same method for the next number, 55, and then 89, and so on.
So, what's the golden ratio? The golden ratio is a special number, approximately equal to 1.618. It appears many times in geometry, art, architecture, and other areas. We can find the golden ratio when we divide a line into two parts so that the whole length divided by the long part is also equal to the long part divided by the short part. Here is a relationship between the golden rectangle and the golden ratio. In the golden rectangle, let's say that one of the sides are, let's just say x, and the other one is y. So over here, x is the longer side, and the y is the shorter side. In the golden rectangle, the side length of the rectangle always has a ratio of 1 to 5, well, approximately 1.618. Where can we find the golden rectangle in nature? Actually, we can find it anywhere. The nautilus shell often displays proportions and dimensions that are close to the golden ratio, appearing in successive rotations of the shell as the shell grows. As well as all living organisms, there is a variation in the dimensions of individual, so the appearance of the golden ratio is not universal. Pine cones and pineapples illustrate similar spirals with successive Fibonacci numbers, with alternating patterns of a spiral and a pine cone. When you correctly place the spiral on a pine cone, it should look like something like this. You can also find golden spiral on, oops, wrong one. Many flower petals are arranged in the golden spiral. This formation follows a scientific formula based on a special sequence of the numbers known as the Fibonacci numbers.